Yes, hello, grade 11s. Good morning today. How are you? This is Patrick Kamala. I want us to go through acids and bases. I'm a tutor here in Pool 1 at Ositaki College 92 Schoolman. You can get us on 0785 222041. Okay. Now, this is the last topic for this term, for the year actually. Acids and bases. Now, we have the terms which we need to understand to understand this topic properly of acids and bases. Now, acids have been discovered a long time ago by different kinds of people. One of them is called Arrhenius, and Arrhenius defined an acid as a substance that produces hydrogen ions or hydronium ions. So if they say define an acid according to Arrhenius, you say it is a substance that produces hydrogen ions or hydronium ions when it dissolves in water. Okay, and then he went ahead to say that a base is a substance that produces OH ions when dissolved in water. So according to Arrhenius, what is a base? It is a substance that produces hydroxide ions when dissolved in water. Now, those definitions of acids and bases were not sufficient as the years went on, because they could not define all the acids and all the bases. That's why there were two people who came together, Rowley and Bronsted, to give us better definitions of the acids and the bases. So according to Rowley, Bronsted, what is an acid? It is a proton donor, period. An acid is what? It is a proton donor. An acid is a proton donor. Now, when we talk about a proton, we mean the hydrogen ion. What is a base? A base is a proton acceptor. A base is what? A proton acceptor. Please be careful. The question will always be specific. They will say, define an acid according to Arrhenius theory, or they can say, define an acid according to Rowley-Bronsted theory. So you must distinguish between the two different definitions. Okay. Apart from that, we have got types of acids depending on how protons donated. One is called monoprotic, then diprotic, and then triprotic. So now a monoprotic acid donates one proton. For example, hydrochloric acid gives us Cl minus plus H plus. Now this hydrogen ion is one proton, and hence this HCl is called what? A monoprotic acid. However, sulfuric acid donates first of all one proton, and then again donates another proton. So 1 plus 2, those are two protons. 1 plus 1, those are two protons, which makes it to be what? Diprotic acid. So sulfuric acid is an example of a diprotic acid. So if they say example of diprotic acid, you must know it is what? It is sulfuric acid, because donates what? Donates two protons. Okay. What about example monoprotic? You know it is what now? It is the hydrochloric acid, because it donates what? One proton. Then if an acid can donate 3 protons, then we call it triprotic. Take an example of this phosphoric acid. Now the phosphoric acid, it has got 3 protons, and at first it donates 1. That's what you see here. This 1 proton first, and then later this one again donates another proton, and then this one also donates another proton, which gives us 1, 2, and 3. So you see, all these are 3 protons. 1, 2, 3. So because there are 3 protons in total, which this phosphoric acid can donate, we say phosphoric acid is a triprotic acid. Okay, another term is to do with the conjugate acid-base pairs. Conjugate acid-base pairs. Now, an acid forms a conjugate base when it donates a proton. So please learners note that whenever we have an acid, okay, after donating a proton, what is left is called what? A conjugate base. That is to say, HA, this stands for the acid. Acid HA donates this proton, so the remainder, which is A minus, is called a conjugate base. Let me repeat. The acid donates a proton, then whatever is left is called what? A conjugate base. Okay, so the acid HA donates this proton, and then what is left is A minus. So the A minus is called conjugate base. Actually, when we say conjugate base, it means that if we start from this side and use this arrow, that conjugate base can also accept a proton, according to Bronsted-Lowry. Okay, and then also note that a base forms a conjugate acid when it accepts a proton. So if a base takes up a proton, what is formed is called a conjugate acid. So in this case, our base, which is A minus, takes up this proton to form a conjugate acid. This is now a conjugate acid here. So conjugate acids and bases differ only by proton. I repeat, the conjugate acids and the bases differ by what? By proton. Okay, example here. Identify the conjugate acid-base pair in the following example. Now this is HNO3 plus water to give us NO3 minus plus hydronium ion. Now check here. This one here, it is nitric, that is HNO3, and this is plus water to give us NO3 minus plus hydronium ion. Now to get what these ones are, you look at the products. If this is NO3 minus, it came from what? From this HNO3, which means HNO3 has donated this proton, so it is the acid A1. It is our first acid because it has done what? Donated the proton. So this is our acid A1. Why? Because according to Bronsted-Lowry, it has donated the proton. Okay, that's our acid A1. And then after donating the proton, we said when the acid donates a proton, this is a proton has donated, then whatever is left is called what? Is called the conjugate base. So this is acid A1, this is our conjugate base B1, because it has remained after the acid has donated the proton. Now note here, this water is H2O, but if you look at the product, it becomes H3O plus, meaning it has accepted a proton. And because I already have a base this side, base B1, which means this is my other base. So this is my other base B2. So this base B2, after receiving a proton, it becomes a conjugate acid. So this is my second acid A2. So this is the conjugate acid A2. So be careful. This is my acid A1. This is my conjugate base B1. This is my base B2. This is my conjugate acid A2. Okay. Now when they are asking you questions here, they can ask you to identify the conjugate acid-base pairs. So your answer can either be A1 together with B1, that forms a conjugate acid-base pair, or the answer can be B2 together with A2, that also forms what? A conjugate acid-base pair. However, the question can also ask only for the acids. If they say identify the acids, in this case you look for A1 and A2. That means it is this HNO3 together with H3O plus. Now the question can also ask for the bases only. In this case, identify for B2 and the B1. So this is H2O and NO3 minus. So there are three ways of asking this question. They can say identify the conjugate acid-base pairs. You take A1 with B1, or you take A2 with B2. Or they can say identify the bases you take B2 and B1, or they can say identify the acids, you take A1 and A2. I hope we are together. Let us proceed. Now, another term which is important to know here in this topic is about ampholyte substance. Okay. Now, an ampholyte substance is that substance that can act either as an acid or a base. I repeat, if we say define an ampholyte, you must know that an ampholyte is a substance that can act as an acid and can also act as what? As a base. So it is a substance that can act as what? Can act as an acid, okay, and also can act as a base. So which means after acting as an acid, then it can again act as a base, as we're going to look at the examples. In other words, the ampholytes or the amphiprotic substances can therefore either donate or accept protons. So note two things, that they can either donate or accept a proton. So now common ampholytes include water, HCO3- and HSO4-. These are examples of the ampholytes. We have water, we have HCO3- and H2SO4-. Now H2SO4- as an ampholyte, check here. Now if it is going to act as an acid, it's going to take up a proton from this water to form, rather it's going to donate a proton from to this water to form SO4 and then this one has accepted, it becomes H3O+. Now if this ampholyte again acts as a base, now it's going to accept a proton from water to form sulfuric acid, that is OH-. Take note of the charges. This is -1, so this side I have -2 plus +1, which gives me -1 generally, finally. So the -1 this side must have a -1 at this side overall. Take here. Now here this is -1, but after accepting a proton from water, the OH remains with the -1. So you see, -1 this side, so they are balanced. So that is how the ampholyte functions. Okay, let us proceed. Let's proceed. Now, another important thing to know here with acids and the bases is to know how you differentiate the concentrated from dilute acids and the bases. Now, what is concentration? It's the number of moles of a solute per unit volume of a solution. That's to say C equals to N over V, or you can use, that's if you have the moles, or you can use concentration equals to mass divided by molar mass times volume. Now, a concentrated acid or base contains a large amount of moles of acid or base in relation to the volume of water. So the question will say, define a concentrated base. You say that it is a base that contains a large amount, of moles of the acid or base relative to the volume of the water. Okay, or you can say in relationship to the volume of water. I repeat, if they say define a concentrated base or acid, you say it is one which contains a large amount of moles of the acid in relationship to the volume of the water. If they say define a concentrated base, then you say it is one which contains a large amount of moles of the base in relation to the volume of water. What about one which is dilute? Now the one which is dilute, it contains a small amount of the moles of the acid. It contains what? A small amount of the moles of the acid or base in relation to the volume of the water. That's how I define a dilute acid or a dilute base. Okay, now examples of that which is concentrated. For the acid, we have 1 mole per decimeter cubed of hydrochloric acid. What about a weak acid? We have 1 mole per decimeter cubed of what? Ethanoic acid. But this weak acid is now concentrated. Although it is a weak acid, it is concentrated. Actually, a weak acid is one which partially ionizes in water. So I repeat, if they say define a weak acid, you say it is the acid which does not completely ionize in water. What about dilute strong acid? Example, I have 0,01 mole per decimeter cubed hydrochloric acid. What about a dilute weak acid? I have an example of 0,01 mole per decimeter cubed of what? Ethanoic acid. Now this case also happens with the bases. That means we have got the strong and weak bases. Okay. Now the strength of an acid or base refers to the ability of the substance to ionize or dissociate. I repeat, the strength of an acid or base refers to the ability of the substance to ionize or dissociate. So if we talk about a strong acid, it will ionize completely in water. Example is hydrochloric acid plus this water. It gives hydronium ions plus chloride ions. So this is strong acid. It gives us the weak conjugate base. Okay, so the hydrochloric acid ionizes with this water to form hydronium ions plus the chloride ion. Hope we are together. However, a weak acid, don't forget this arrow is a full arrow, and it is only in one direction. However, a weak acid will only partially ionize in water. Take an example of the carbonic acid. In water to ionize, it gives us hydronium ion plus the carbonate. Now, the weak acid forms a strong conjugate base. Okay, so that that carbonate here, aqueous, it can combine again with this hydronium ion to form back the reactants. So in this case, yes, hello. Okay, I'm saying that take a note that a weak acid will only partially ionize in water. So you see this double arrow, the first arrow shows that the reactants give us products. But because the formed products are strong, they can form back the reactants. That's using this other arrow. So this arrow is for the partial, meaning that a weak acid will only partially ionize in water. Okay, don't forget, a strong acid forms a weak conjugate base. In other words, we cannot have a reverse reaction possible. But a weak acid, it forms a stronger conjugate base such that we can have a reverse reaction possible. Okay, then bases, we have a stronger base will dissociate completely in water. For example, sodium hydroxide is a strong base. It dissociates to form sodium ions plus OH ions. Now if we say dissociate, we form, it's like we split the sodium hydroxide to give us the sodium ion plus OH ions, hydroxide ions here. Now the stronger base, note it dissociates to form a weak conjugate acid. Okay, so because this is a weak conjugate acid, it means it cannot donate the proton. Okay. Note a weak base will dissociate only partially in water. For example, magnesium hydroxide dissociates to give us magnesium 2 ions plus 2 hydroxide ions. That is to say, the weak base dissociates partially to give us a strong conjugate acid. So because it has formed a strong conjugate acid, it means the reverse reaction is possible. Now ammonia is an exception of the bases. Now the bases, we've seen that they dissociate, but ammonia ionizes. So ammonia ionizes to form hydroxide ion plus ammonium ion. So ammonia is an exception because it ionizes just like the acids. Don't forget the bases dissociate except ammonia, which ionizes. Let us proceed. Let us proceed here. Now if we proceed here, we have the influence of the acid and the base strength. Now, how does the strength of the acid and the bases influence the reaction rates? Now, the reaction rates increase as the strength of the acid or base increases. Don't forget that a strong acid ionizes completely in water. What about a strong base? Dissociates completely in water. So reaction rates increase as the strength of the acids or bases increases. A strong acid is equivalent to a higher concentration of ions, and in that case we get a greater rate of reaction. And so does conductivity. The conductivity increases as the strength of the acid or base increases. So a stronger acid leads to a higher concentration of protons and hence a greater conductivity. Here we have the common acids and the common bases, which they ask in your exam. You must know the formulas and the names as well. This is hydrochloric acid and the nitric acid. Hydrochloric acid is HCl and the nitric acid is HNO3 and sulfuric acid is H2SO4. Now these three are what we call as the strong acids. So the strong acids include hydrochloric acid, nitric acid, and sulfuric acid. Don't forget, you must know how to write the formulas as well, because you must know them in your test and exam. And then we have what we call as the weak acids. The weak acids, they are carbonic acids actually. Those ones include oxalic acid, hydrofluoric acid, sulfurous acid, carbonic acid, acetic acid, also called ethanoic acid, and then phosphoric acid. Now we said that the weak acids only partially ionize in water. Remember, the double arrow is to do with the weak acids, which partially ionize in solution. Then on the side of the bases, the group 1 elements, that is the sodium and the potassium, they form what we call as the strong bases. We say that strong bases completely dissociate in solution. Okay, so these are the strong bases. Now the weak bases include sodium hydrogen carbonate and the sodium carbonate and the sodium and the ammonia. Okay, so now the weak bases include what? Sodium hydrogen carbonate, that is NHCO3, and the calcium carbonate CaCO3, and the sodium carbonate, that is Na2CO3, and the ammonia, which is NH3. So these are the weak bases and the others which are not group 1 element, which are not group 1 bases. Okay, those are also weak bases. Let's talk about the pH scale. The pH scale, the pH of a solution is a number that represents the acidity or alkalinity of a solution. The greater the concentration of hydrogen ions in solution, the more the acidic the solution and the lower the pH. I repeat, we are saying that the greater the concentration of hydrogen ions in solution, it means what? It means the more acidic the solution is. The more acidic the solution is, and the lower the pH. Are we together? However, the lower the concentration of hydrogen ions in solution, the more alkaline the solution and the higher the pH. So the higher pH has got a lower concentration of hydrogen ions. Now you must know that the pH scale ranges from 0 to 14 and is a measure of the hydronium ions at 25 degrees Celsius in water. The formula for getting pH, as we shall see the calculations ahead in grade 12, it is pH equals to negative log of hydronium ion concentration. So this side is for the acids, in the middle is neutral, then the bases. So the range from 0, 1, 2 up to 14 is the pH scale, and from 0, here we have the strong acids this side, and then weak bases beginning from 4, 5, and 3 and 6. 4, 5, and 6, these are weak acids, yes. 4 with pH 4, pH 5, and 6, those are called weak bases. Now, weak acids, sorry. And then the bases which are closest to the neutral pH, which is 7, they are the weakest bases. So bases with pH of 8 and 9 and 10 and 11, we call them weak bases. And then those ones which are strong, they have got 12, 13, and 14. Those are strong bases which we can see using the pH scale. I hope we are together. Let us proceed. Now again, this topic of acids and bases has got other important information which you need to know about hydrolysis of salts. Okay. Let us look at the reaction of acids. Now acids do react. Acid reactions are reactions during which protons are transferred. When we have an acid plus a metal, we get a salt plus hydrogen gas. For example, nitric acid, that's the acid Ha, plus our metal sodium, it gives us sodium nitrate plus hydrogen gas. So please note for your tests that when you react an acid plus a metal, you get a salt plus hydrogen gas. However, when you react an acid plus a metal hydroxide, that's a base, you're going to form a salt and water. For example, sulfuric acid plus magnesium hydroxide, it gives us magnesium sulfate, which is a salt, plus water, that is H2O. Also note that when you react an acid plus a metal oxide, then you form a salt plus water as well. For example, hydrochloric acid reacting with magnesium oxide, it gives us magnesium chloride, which is the salt, plus water. However, if you react an acid with a metal carbonate, then you form a salt plus water, but also carbon dioxide gas. An example is hydrochloric acid plus calcium carbonate. It gives calcium chloride plus water plus carbon dioxide gas. Now, the ionic salt is made up of A- from the acid and is made up of M+ from the base. Okay, hope we are together. Now, we also have what we call as titrations. Now, a titration is a practical laboratory method to determine the concentration of an acid or a base. The concentration of an acid or a base can be determined by accurate neutralization using a standard solution. What's a standard solution? It's a solution of known concentration. So in your test, if they ask you to define a standard solution, you tell them it is a solution of known concentration. That is a standard solution. And then neutralization occurs at equivalence point when the acid or base has completely reacted with the base or acid according to the molar ratio. That is to say, this formula is very important in our calculations. We're going to see the examples. Na divided by Nb equals to Ca times Va divided by Cb times Vb. Na means number of the molar ratio of the acid divided by the number of the molar ratio of the base equals to concentration of the acid times volume of the acid divided by concentration of the base times volume of the base. We are saying that N is number of moles of the substance, which can be a base or acid. That's we mean the molar ratio from the balanced equation. And then C is the concentration of the acid or base in moles per decimeter cubed. What about volume? Is the V. Now also note that in our calculations, 1 milliliter means 1 centimeter cubed, and 1 liter stands for 1 decimeter cubed, and 1,000 milliliters represent 1 liter, and also 1,000 cubic centimeters also 1 decimeter cubed. Let us proceed. This topic is so interesting, isn't it? Now again we have to call as hydrolysis of salts. Hydrolysis of salts. Now hydrolysis is the reaction. They will say define hydrolysis. They will say define hydrolysis. It is a reaction of an ion with water. If they say define hydrolysis, you say it is what? It is a reaction of an ion with water. Now during hydrolysis, the salt will form an acid, alkali or neutral solution. The pH of the salt solution is determined by the relative strength of the acid and the base that is used to perform the salt. I repeat, during hydrolysis, the salt will form an acidic or alkali or neutral solution, and then the pH of the salt solution is determined by the relative strength of the acid and the base that is used to form the salt. Okay. All right. Now this is what happens here. If I react a strong acid with a weak base, then my resultant salt is going to be acidic. I repeat, if I react a strong acid with a weak base, I'm going to get my resultant salt to be acidic. However, if I react a strong acid with a strong base, I'm going to get a neutral salt. And if I react a weak acid with a weak base, still I get a neutral salt. If I react a weak acid with a stronger base, however, my resultant is going to have what? An alkali salt. Hope we are together. Let us continue here. We're going to look at examples, how to determine the pH of a salt. Okay. Now, take an example of this ammonium chloride salt. Now, ammonium chloride gives me ammonium ions in solution plus chloride ions. Now, the ammonium ions combines with the water, this is now hydrolysis, to form ammonia plus hydronium ion. Okay, and then the chloride ion, which you see here, also reacts with this water to form HCl plus what? Plus OH minus. Are we together? Don't forget that the ammonia NH3 is a weak base. Okay, and then equilibrium lies to the right, and so we have a higher concentration of hydronium ions. Okay, we have what? A higher concentration of these hydronium ions because this is a weak base. Okay, and then so for that matter, it means our HCl is a strong acid, and then equilibrium lies to the left. Okay, so we have a low concentration of what? OH ions, and then we have a high concentration of hydronium ions and a low of OH ions. So for that matter, it means that this sea salt, which is ammonium chloride, is acidic, and hence the pH is less than 7. You can say, what do you mean exactly? What I mean is that because I have a high concentration of hydronium ions and a low concentration of OH ions, my pH is going to be less than 7, and because less than 7 from the pH scale is going to be acidic. So ammonium chloride is an acidic salt in water. Let us check something else here. Let us look at the sodium carbonate. Now, sodium carbonate salt in water gives us sodium ions plus carbonate ions. So the sodium ions, these ones, they combine with the water to form sodium hydroxide plus the proton. And then the carbonate ions combine with the water. This is hydrolysis, to form the carbonic acid plus OH ions. Don't forget that the sodium hydroxide is a strong base, and because of that, I'm going to have my equilibrium lying to the left, meaning it's going to be this side. Okay, it means this reverse action it proceeds much more than the forward. If I say my equilibrium is to the left, I mean what? I mean that the products formed, they react to give me back the reactant C. And then note that the carbonic acid is a weak acid, and in that case equilibrium lies to the right. So you see this carbonic acid, it's a weak acid. So because of that, it means that this equation is going to yield more of the products, and I won't have the reactants back like in the previous equation. So for that matter, I'm going to have a high concentration of OH ions. You can say why? Because for this equation, for this reaction, my equilibrium lies to the right, because this is a longer arrow, meaning that I'm going to have a higher concentration of OH ions, and because of that, I am going to have my pH bigger than 7 and hence alkali. So because of the low concentration of hydronium ions and the high for the OH ions, I'm going to have sodium carbonate aqueous to be an alkali solution or salt. Hope we are together. If you're not together, pause the video and watch it again. Okay, let us proceed. Now, if the salt is an acid or a base, we use indicators to indicate that. Okay, so what are indicators? An indicator is a compound that changes color according to the pH of the substance. During titrations, the indicator needs to be selected according to the pH of the salt solution that would be produced. Okay, as we have seen hydrolysis. Now, these are the indicators which we have and their corresponding pH colors and the pH ranges. Okay, now the litmus is red in acidic pH, and it is blue in the base. And the range for the litmus is what? It's between 4,5 and 8,3. That is the pH range for the equivalency point. And then if I talk about methyl orange is red in acid, and methyl orange is yellow in what? In the base. And then at equivalence point, it turns to orange. And the pH ranges from 3,1 to 4,4. And then bromothymo blue is yellow in the acid, and bromothymo blue is blue in the base. And then at equivalence point, it turns green, and the pH range is from 6,0 to 7,6. And then lastly, we have what we call as the phenolphthalein indicator. Phenolphthalein indicator is colorless. It's a clear solution, just like a water, the clear water which you drink. Okay, so it is colorless or clear in acid, but in the base it is pink, and then at equivalence point it appears pale pink. And then the range for the pH equivalence, it is from 8,3 to 10,0. Okay, and then the neutral pH is 7. Now, what is neutralization? Neutralization is when the equivalency point is reached. Equivalency point is known when the solution is at pH 7, but when the acid and the base has completely reacted with the base or acid according to the molar ratio. The pH at neutralization is dependent on the salt that is formed, as we have seen in hydrolysis, whether it's going to be a base or, you've seen here, if you have got more of the OH ions, it's going to be alkali, but if you have got more of the hydronium ions, it's going to be acidic. Okay, Alright, now let us look at the titration setup here. Now when we are titrating, we have what we call as a burette. We put the acid in here, and then this is a stop cork, and this conical flask, and then we have the base and the indicator in here. So we titrate and put the volume of the acid here, put the acid in here, and then we open the stop cork, and then as the acid flows into the conical flask, we swirl. We swirl it, we shake it and swirl it, and as we swirl it, we are going to have to reach equivalency point. Remember there is a base inside here, so the acid plus the base, as you continue adding the acid, you're going to reach what we call as the equivalency point, and that process is called what? Titration. And at equivalence point, when you have the indicator in here, it's going to have a change in color. In other words, you're going to see your colors like this. At the equivalence point, you're going to see either you're going to see the yellow if you use the methyl orange, or you're going to see blue if you use the bromothymol blue, or you're going to see pink if you use the what? Phenolphthalein indicator in the conical flask. Okay. Now the burette is what we use to get a specific volume of the acid that has been used to neutralize the base, which is the conical flask. Okay. Now note something that a pipette is the procedure was like this. You pipette a specific amount of the standard solution into a conical flask. What did we say is a standard solution? The one with a known concentration, right? And then you add an appropriate indicator to the flask according to the pH of the final solution. And then what do you do next? You fill the burette with a solution of the unknown concentration, usually the acid and the burette, and then you add the solution from the burette to the conical flask at a dropwise rate. Okay, remember to swirl, to rotate the conical flask, to swirl, and then you stop the burette when the indicator shows neutralization. That means that the equivalency point has been reached. That's when you stop releasing the acid into the conical flask. So that's to do with titration. I think you see it at school when your teacher is doing like that. Now we have to look at examples here. For such calculations, they carry a lot of marks, but very easy anyway. Now during a titration, 25 centimeters of dilute sulfuric acid neutralizes 40 of sodium hydroxide solution. I repeat, during a titration, 25 cubic centimeters of dilute sulfuric acid neutralize 40 cubic centimeters of sodium hydroxide solution. They say if the concentration of the sulfuric acid solution is 0.25 moles per decimeter cubed, calculate the concentration of the sodium hydroxide. Now, I repeat this question again. They're saying that during a titration, we have 25 cubic centimeters of a dilute sulfuric acid, and they neutralize the 40 cubic centimeters of sodium hydroxide solution. So this is our acid, this is the base, and this is the volume of the acid, this is the volume of the base. All together, they say if the concentration of the acid solution is 0.25 moles, so now the concentration of the acid, that is the Ca, is 0.25 moles per decimeter cubed. They say calculate the concentration of the base. So I'm looking for Cb. Now the formula for sulfuric acid is H2SO4 plus sodium hydroxide, which is NaO4, NaOH, to give us sodium sulfate plus water. Please, you must balance the equation. Now I know my Na is 1 because of the one here. Okay. And then my Nb is 2 because of the 2 here for the base. Then the C for the acid, that is Ca, it is 0.25, this is given here. And then the C for the base is what I'm looking for. Volume for the acid used, it is 25 cubic centimeters, but I must divide by 1,000 because I must have it in decimeters cubed. That's why it's like this. And then the volume for the base, it was 40, which is going to be 0.04 decimeters cubed as well. So now, after having this information, I have got two methods to use. I can either use the titration equation, that is to say NA over NB equals to CAVA divided by CB times VB. I'm substituting. Now I'm looking for CB here. Then if I cross multiply, I can surely get my base concentration as 0.31. Or if I use first principles, I know that number of moles for the acid equals to C times V, 0.25 times 0.025, which gives me 6.25 exponent -3, and then from the base C equals to N over V, so I can get N over V. That means the 6.25 exponent -3 times 2 divided by what? By 0.04. Why do you multiply by 2 here? Because our mole ratio between the acid and the base was 1 to 2. So if I know the moles of the acid, to get moles of the base, I multiply by 2. That's why I am multiplying here by 2 here. This 2 here. So you see I get the same answer, which is 0.31 here as well as here. Hope we are together. Hope we are together. All right, so let us continue. So now, acid and bases, please do as many examples as you can, because these questions, they are so interesting and they carry a load of marks. Okay, let us continue. Now, more to the acid and bases, the redox reactions. Redox reactions. What's a redox reaction? It's a reaction in which there is a transfer of electrons between elements. So they are going to ask you, students are going to say, define a redox reaction. What will you tell them? That it is a reaction in which there is transfer of electrons between elements. So a redox reaction involves the transfer of electrons between elements. And another term you know here must be oxidation, which is the loss of electrons. And in this case, the oxidation number increases. And then reduction is the gain of electrons. And in this case, oxidation number decreases. The oxidizing agent is the substance which accepts electrons. Please understand this when you say define oxidizing agent. You must tell them it is a substance which does what? Which accepts protons. And it's the substance which is reduced and it causes the other substance to be oxidized. What about reducing agent? It is a substance that donates the electrons. So if they say define a reducing agent, you must know it is one which donates electrons. Now, these acronyms here, they help us to remember these definitions properly. In your test, you can use them as well. Oil, it means oxidation is loss of electrons. What about ridge? Reduction is the gain of electrons. Or you can use LEO, meaning loss of electrons is oxidation. Or GL, which means gain of electrons is reduction. Okay, don't forget that. Let's talk about oxidation numbers. Now, in order to keep track of the electrons during a chemical reaction, oxidation numbers are assigned to each element in the reaction. The oxidation number is similar to the valence of the element. Please, before these rules, when we are assigning oxidation numbers, rule number 1, the pure elements and the diatomic elements have got oxidation number 0. For example, oxygen. And then hydrogen has got +1, with the exception when bonded to a metal, then it becomes -1. Okay, for example, sodium hydride. Now here, oxygen has got -2, with an exception in the peroxides where it becomes -1. And then when bonded to fluoride, it becomes +2. Okay. Then with the metals, the group number gives us oxidation state. For example, group 1 gives us +1. Group 2 have got +2 oxidation state. What about group 3? They have +3. The oxidation number of monoatomic ions is the same as its charge. For example, the zinc 2 ions, its oxidation number is +2. And group 17 have got -1 oxidation state. Rule number 7. The oxidation number of transition metals is indicated by Stoke notation. For example, iron 3 chloride, this 3 shows as the oxidation number, so it is +3 for this iron. And in a neutral compound, the sum of the oxidation numbers is 0. In a neutral compound, the sum of what? The oxidation numbers is 0. We're going to see that in the examples to come shortly. And then in a polyatomic ion, the sum of the oxidation numbers is equal to the charge on the ion. We're going to see that in the examples as well. Example here, they say, give the oxidation number of each of the elements in the following. This is oxygen. You see, it's not combined, so it's going to be 0 here. And then that's for the oxygen. It is 0. Now here we have hydrogen sulfide. In this particular case, hydrogen is going to be having +1. What about sulfur? It's going to be -2. Now there is a 2 on hydrogen here. 2 times +1, it is +2. +2 plus -2 gives us 0. So you see, this one is not bonded, so it is neutral. In that case, that's why sulfur is -2. Then in potassium permanganate, note here that potassium is in group 1, so it has got +1 oxidation state. Are we together? What about oxygen? Oxygen group 6 has got -2 oxidation state. Then the manganese, that is Mn, it has got +7 oxidation state. Maybe somebody can say, how do you get those answers, right? Let me show you one here. For manganese. Now note that in this case, for potassium, okay, I'm going to that. Let oxidation state for manganese be any letter. I'm going to use Y. So because here this is 0, this is neutral, it's not like here which is charged and which is charged here. So if I add all oxidation states here, I must get 0. So the one for potassium is 1 because in group 1, that is +1, okay. And then the one for manganese, I said let it be Y, okay. And then the one for oxygen, it is -2, but how many are they here? There are 4 of them, so it's going to be 4, open brackets, then -2, okay, -2. Now when I add all of them here, I must equate to the 0, which is what you see here on top here. So now look here, it means I have 1 Y here plus Y, okay. So what is 4 times -2? That's -8, okay, equals to 0, okay. And then what is 1 minus 8? That's -7. So -7 plus Y equals to 0, which gives me my Y as what? As +7. So this +7 is the oxidation state which is for manganese. That's why I saw that manganese there was having +7 here. That's how we calculate it. If I come to sulfate here, and I want to get the oxidation states in that case. Now with oxygen, I know, because this is not peroxide, I know it's -2. So for sulfur, if I want to know whether it is +6, and I don't know, what do? I can say, let oxidation state for sulfur be, and the letter may be X. So I'm going to say X, okay, and then plus the one for oxygen, but there are 4 here, plus 4 multiplied by minus 2, and then I'm going to equate to what? I'm going to equate to the charge. Now my charge here, as you can see, it's -2, equal to -2. Okay, so it's going to be x. Now if I multiply 4 times negative, it's going to be -8. Everything equals to -2 here because that's our charge here overall. So the x equals to -2 plus 8. What do you get? Talk to me now. -2 plus 6 gives me what? I mean plus 8 here gives me +6, right? Gives me +6. I repeat. It's supposed to be what? It's supposed to be 8 here, and 6. Okay, so it means I must be having 8 here. Okay, so that 8 minus 2 gives me my x as what? My x as +6. So in this particular case, sulfur has got +6 oxidation state, which you see here. Are we together? Now for iron and the chlorine here, because chlorine has got -1, iron must be having +3 here, because of the 3 here on chloride means it was 3 times -1, -3, and because this is 0 here, it means to have -3 neutralized, the iron must be having +3. I hope we are together. Let us proceed. Let's proceed. And then now how to represent redox reactions? Redox reactions can be shown in 2 half reactions showing the transfer of electrons. We are able to call as the oxidation half reaction and then reduction half reaction. What is oxidation? We say it is gain of electrons. What about reduction? Loss of electrons. So in this case, X to give us X2 plus 2 electrons, it means it has gained. When we gain, electrons appear on the products. When we lose, here in the reduction, they appear in the reactants. What about an oxidation? They appear in the products. Okay, so this is the net reaction here, whereby the 2 electrons cancel out as we add to get the overall equation. So when I add the oxidation half reaction plus the reduction half reaction, the electrons are going to cancel out, left with x plus y, which you see here, then plus this xy plus what? Plus xy, because this x2 minus and y2 minus combined to give me xy here. So no electrons are shown in the reaction, which is the overall. Okay, example here, they say in the following equations identify the oxidizing and reducing agents. Okay, so step 1. Now this is copper oxide plus hydrogen to give us copper plus water here. If you check here, this is copper with its oxidation state. Now this is oxide, which was having 2 minus. This is copper 2, that's with the +2. What about here? Hydrogen has got +1. What about oxygen? -2. If you check here, the copper 2 has changed from +2 to 0. So there is a reduction in oxidation state number. Okay, and then what about the oxygen? Oxygen, this is 2 minus, it's the same. What about hydrogen? It's getting from 0 to +1. So it's that for copper, it has been changed from oxidation state +2 to 0. What about oxygen? It remained constant. What about hydrogen? From 0 to 1. So in this particular case, because I want to identify the oxidizing and reducing agents, this is what happens in the next step. The copper 2 ions, oxidation number decreases, net has gained. And then electrons have been reduced, so it's oxidizing agent. So the copper 2 ion is the oxidizing agent. Why? Because it has reduced from 2 to 0. so it becomes the oxidizing agent. And in hydrogen, it has been increased from 0 to +1, it becomes the reducing agent. So in other words, the one which loses electrons becomes reducing agent, and then the one which gains becomes oxidizing agent. Okay, that's how we identify the reducing agent and oxidizing agent here. I think we deserve another example. Let's check it out here. Now in here, nitrogen monoxide plus carbon monoxide gives nitrogen plus carbon dioxide gas. You see here, oxygen has got 2-. What about nitrogen? +2. What about here? This is 2- for oxygen, then +2 for carbon. What about the product? This nitrogen is now it is 0. What about carbon dioxide? Carbon is now +4. What about oxygen? It is still 2-. So oxygen is the constant, 2-, has not changed. And then nitrogen has changed from +2 all the way to 0. It has decreased in oxidation state. What about carbon? From +2 to +4. That's what you see here. So for that matter, note this now. Nitrogen, what about its oxidation number? It's from +2 to 0. So it has reduced. Okay. So in this particular case, nitrogen becomes the oxidizing agent. Becomes what? Oxidizing agent. Why? Because it has oxidized the carbon from +2 to +4. Check, from +2 to +4. What has done that? It is nitrogen monoxide. So nitrogen monoxide, NO or N2+, is called oxidizing agent. And then the carbon, which is the C2+ or CO, its oxidation number has increased. Okay, so it becomes the reducing agent. Why? Because the carbon 2+ has reduced the oxidation state of nitrogen from +2 up to 0. So it means that in this particular case, my carbon monoxide, or you can call it C2+, is called what? The reducing agent. Okay, we are almost done, don't worry. Now another example here, it says write the balanced redox reaction for the following reactions here. This is magnesium plus iron sulfate to give us magnesium sulfate plus iron. Okay, now I'm going to first identify my oxidation states here. Magnesium, it is 0. What about iron sulfate? It is 2 for the iron. Sulfur +6, then oxygen -2. What about magnesium sulfate? It is 2 for Mg, then 6 for sulfur, and then -2 for oxygen. What about iron? It is 0. Okay. Now note something here, that with magnesium, it's getting from 0 to +2. You see this is 0 here, and this is +2. Okay. What about iron? It's getting from +2 to 0. Sulfur and oxygen remained the same, 6, 6. Okay, so for that matter, it means that because I want to write the balanced redox reaction for the following reaction, I consider those which have got the transfer of electrons. We said, what's a redox reaction? One involving transfer of electrons from one element to another. So in this particular case, it means I'm going to be having the transfer of electrons between magnesium and iron. So it means that in this particular case, magnesium oxidation number increased, it lost. What about iron 2? Decreased, it reduced. Okay, so it gained, which means that magnesium Mg undergoes oxidation to give me Mg2 plus 2 electrons. What about iron 2? It undergoes reduction to give me iron here. Okay, so this is oxidation, this is reduction. Because I've got the same number of electrons, when I add the two equations, I'm going to cancel this one with this one here to get my overall equation. Okay, so as you can see, I'm cancelling these 2 electrons with this one here, and I'm left with the Mg plus Fe2 plus which you see here, to give me Mg2 plus Fe. So this is my overall net redox equation. Our last example, this one here, it goes like this. The question still says that write the balanced redox reaction for the following reactions. That is to say, zinc plus silver nitrate to give me silver plus zinc nitrate. Okay, now zinc gets from 0 to positive 2. What about silver? From positive 1 to 0. Okay, what about the others? They are having the same, that's minus to minus 2. So it means in this particular case I'm going to have my oxidation to be, because zinc got from 0 to positive 2, so zinc has been oxidized from 0 to positive 2. That's why it loses electrons. What about my silver? It has gained from positive 1 to 0. So now, because this is 2 and this is 1 and this is 2, I must balance before I cancel the electrons. So it means I'm going to multiply by 2, and when I do so, I'm going to have something like this. I'm going to have here, I'm going to multiply 2 by 2 here to balance the electrons. Remember that these are 2 electrons here for zinc. Okay, so I must multiply by 2 here. Okay, and multiply by 2 here, and multiply by 2 here. So when I'm going to add, I'm going to cancel these 2 electrons with these ones here. So as I add, I cancel these 2 electrons with these ones here to get my overall. So it's going to be zinc, which you see here, plus 2 silver iron plus to give me zinc 2 ions plus silver. So that is my overall net redox equation. Okay, so this is my redox equation, which is called the net. It is formed by adding 2 half reactions of the oxidation and reduction. Hope we are together. Okay, thank you so much for watching. Please try these questions here. And if you find any challenges, put up your hand if you are attending the extra class, or you can inbox me on 0785 222 041, or you can simply come to Rostake College on 92 Skuman to see how you get the answers to these questions and get your marks. And why not then go to grade 12, because this is the last part of the paper. Are we together? This question was also done. Please try it out. I'm sure you can answer these questions now. Try them out. And then this other one here, the last part of the question, also try it out. Yes. Thank you so much for watching. Once again, my name is Patrick Kamala. I'm a tutor and educator for mathematics and physical sciences